Good afternoon, everyone. I hope that you all had a fantastic weekend and that you're doing well today. Welcome to the beginning of the final week of this little journey that we've found ourselves on together. What we're going to be doing this week is learning how to integrate using something called partial fractions. And this lesson can be found on page 24 of your lesson handout. So what partial fractions involves is the integration of rational expressions. Depending on the structure of the rational expression, the exact steps involved in using partial fractions varies. So I would like to take a second and explain something to you about what we are learning today. When you integrate a rational expression, if the rational expression has the following two properties, then you can do what we're going to learn today. All of the rational expressions we will integrate today, first of all, have a numerator that has a degree smaller than the denominator. If the degree in the numerator is not smaller than the denominator, then you would have to use a technique that we will learn in Friday's lesson. The second property of the rational expression, in order to use what we're going to learn today, is that the denominator, as well as having a higher degree than the numerator, must be factorable and the factors must be linear. So let's keep that in mind. At the end of today's lesson, you will have all of the ammunition you need to complete your final assessment, which means that what we are going to learn on Wednesday and what we are going to learn on Friday is not necessary for your final assessment, and therefore you don't really need to complete those lessons. However, as a teacher trying to get you ready for post-secondary, I think I would be negligent if I didn't go over the other situations. So on Wednesday, what we will be looking at is, among other things, what happens if the denominator is not factorable into linear factors. And on Friday, I will be looking at what happens if the degree on the numerator is not smaller than the degree on the denominator. But again, you are only expected for this new modified course to know what we learned today. However, what we learn Wednesday and Friday will be helpful for those students who are going to go on and take calculus next year. So, most rational expressions can be integrated using the method of partial fractions. I would probably say that you could probably go through 2 full years of post-secondary calculus and not run into a rational expression that cannot be integrated using this method. But they do exist. The whole goal in using this method is to take the integrand, which is a rational expression, and rewrite it as a sum of simpler rational expressions. As an example, the rational expression 11x plus 7 over x squared plus 4x minus 5 happens to be exactly equal to 3 over x minus 1 plus 8 over x plus 5. What that means is if you were to pick any number in the universe that's a permissible value for x in the rational expression 11x plus 7 over x squared plus 4x minus 5 and put it into that expression, you would get the same result as you would if you put that number into 3 over x minus 1 plus 8 over x plus 5. They're exactly equal to each other. I do want you to notice something about this rational expression. This rational expression has a linear polynomial in the numerator, which means the degree of the numerator is 1. And the denominator is quadratic, which means the degree of the denominator is 2. And that means that the degree in the numerator is smaller than the degree in the denominator. I also want you to notice that x squared plus 4x minus 5 is factorable into 2 linear factors. So this is the type of rational expression we are learning how to integrate today. So if we wanted to integrate 11x plus 7 over x squared plus 4x minus 5, our brain looks at that and hits a brick wall. We cannot look at that and say to ourselves, oh, I know exactly what the antiderivative of that is, because it's almost impossible to formulate what you would differentiate to get that. However, and we will look at the exact answer to this problem in a bit, our brain looks at the integral of 3 over x minus 1 plus 8 over x plus 5, and we do not hit a brick wall there. We know exactly what we have to do to integrate that. And if those two integrands are equal, then if we find the integral of 3 over x minus 1 plus 8 over x plus 5, we will have found the integral of 11x plus 7 over x squared plus 4x minus 5. All right, taking a look at the warm-up, the first part of the warm-up is asking us to show that 11x plus 7 over x squared plus 4x minus 5 is in fact equal to 3 over x minus 1 plus 8 over x plus 5. So let's take 3 over x minus 1 and add to it 8 over x plus 5. Of course, when you add rational expressions, just like adding any other fractions, what you need to do is make use of a common denominator. And the least common denominator here would be the product of those two denominators, x minus 1 and x plus 5. So what we are going to have to do is multiply the numerator and denominator of the first rational expression by x plus 5, and multiply the numerator and denominator of the second rational expression by x minus 1. That allows us to bring those two rational expressions together with a single common denominator of x minus 1 multiplied by x plus 5. On the numerator, we're going to have 3 multiplied by x plus 5 plus 8 multiplied by x minus 1. So now what I'm going to do is simplify the numerator by expanding it out. 3 times x is 3x plus 3 times 5 is 15. Then I have 8 times x, which is 8x, and I have 8 times negative 1, which is negative 8. I'm also going to expand out the denominator by foiling out x minus 1 times x plus 5 to get x squared plus 5x minus 1x minus 5. So what we end up with is in the numerator 3x plus 8x, which is 11x. We also have 15 minus 8, which is plus 7. And in the denominator, we have x squared plus 4x minus 5. So we have just shown that 3 over x minus 1 plus 8 over x plus 5 is in fact equal to 11x plus 7 over x squared plus 4x minus 5. And that means, for the second part of the warm-up, if you were asked to integrate what I've highlighted in blue, what we can do instead is integrate what I'm highlighting in yellow. Because if those two integrands are equal, then the integrals are equal. And integrating the thing that we have in yellow is child's play. The antiderivative of 3 over x minus 1 is 3 ln of x minus 1, plus the antiderivative of 8 over x plus 5 is 8 ln x plus 5. It should be pretty obvious that if you differentiate 3 ln x minus 1, you're going to get 3 times 1 over x minus 1, which is what we were trying to anti-differentiate. And if you differentiate 8 ln x plus 5, you're going to get 8 times 1 over x plus 5, which is also in what we were trying to anti-differentiate. Of course, we have our constant. So this is what the integral of 11x plus 7 over x squared plus 4x minus 5 is equal to. Of course, you don't go directly from the blue integral to the answer in red. You have to change the blue integral to the yellow integral so that you can make sense of it. The rest of this lesson is going to be showing us how we can do that. How can we take a rational expression and tear it apart into smaller pieces that are added together? Example 1 asks us to integrate 5x plus 1 over x squared plus x minus 2. Now, to begin with here, you need to understand that this method, called the method of partial fractions, is not about learning how to integrate. What it's primarily about is learning how to take a rational expression like 5x plus 1 over x plus 2, x minus 1, and write it as a sum of two partial fractions. So you'll notice that I took the liberty here of factoring the denominator. X squared plus x minus 2 factors into x plus 2x minus 1. I want to point out to you that this integrand has a degree of 1 in the numerator and a degree of 2 in the denominator. So the degree in the numerator is smaller than the degree in the denominator. That's one of the conditions necessary for what we learned today to work. The other thing I want you to notice is the denominator is factorable. That's the other condition. And again, if you were to go to your final assessment, one of your integrals that you're asked to find is going to fall into this category. Smaller degree on the top, bottom is factorable into linear factors. Now, if that is the case, then the number of partial fractions will be equal to the number of factors in the denominator. So if we have two factors in the denominator, we're going to have two fractions that we can add together to get that. The other thing that you'll note is the two fractions have to have denominators that match the factors in the old denominator. And I don't want to get into why, but in this particular situation, the numerator of each of your partial fractions will be a constant. So whatever capital A is, it's a number. Whatever capital B is, it's a number. And what your goal is to find out what A and B are equal to. Because if you knew what A and B were equal to, you could rewrite that integral using the equivalent statement on the right side of this equation. Now, how do we go about finding the value of A and the value of B? We're going to start off by multiplying both sides of this equation by x plus 2, x minus 1. So we have to multiply both sides by that. What we're doing here, everybody, essentially is eliminating the denominators. And if we were in class together, I probably would skip this next step, but I don't want to leave anybody in the dirt here. What I then have is I have 5x plus 1 multiplied by that x plus 2, x minus 1, and it's over x plus 2, x minus 1. I need to take on the other side this x plus 2, x minus 1, and distribute it by multiplying that by the a over the x plus 2 and multiplying that by the b over the x minus 1. Which means I'm going to have my a over my x plus 2, and then I have to multiply that by x plus 2, x minus 1. Then I have plus b over x minus 1, and I need to multiply that by x plus 2, x minus 1. And I think most of you would not need to write this step. What's going to happen here is on the left-hand side, the x plus 2 and the x plus 2 cancel, the x minus 1 and the x minus 1 cancel. In the first part of the right-hand side, the x plus 2's cancel, but the x minus 1 does not. And in the second part of the right-hand side, the x minus 1's cancel, but the x plus 2 does not. And what that leaves us with is 5 multiplied by x and then plus 1 is equal to a multiplied by x minus 1 plus b multiplied by x plus 2. And I would suppose that most people would be capable of going from this point directly to this point without having to show that expansion. Now, how are we going to use this to find a and b? There are a couple of methods that you can use now to find a and b. I'm going to show you the simplest, the quickest. There is a more analytical approach involving systems of equations, but I don't want to do that. So what we are going to be doing is the following. I'm going to let x equal 1. Now, why am I doing that? Well, if I let x equal 1, then I'm going to have on the left-hand side 5 times 1 plus 1. And on the right-hand side, I'm going to have a, and then in brackets, I'll have 1 minus 1. This is why I'm choosing x equals 1. Because if I do choose x equals 1, this entire term becomes 0. On the other hand, with the second term, I'm going to have b and then multiplied by 1 plus 2. This is going to leave me with an equation that I can use to solve for b. On the left-hand side, I have 6. On the right-hand side, I have 0 plus 3b, which means that 3b equals 6. And I can divide both sides by 3 and get b equals 2. Now what I'm going to do is the exact same thing, but I'm going to choose a value for x that will make the b's go away. So when I look at this line, the value of x that would make the b's disappear from our lives temporarily would be -2. Because if I put -2 in for x, the second term will be b multiplied by -2 plus 2. So I'm going to let x equal now -2, and what that's going to produce, don't forget on the left-hand side I had 5x plus 1, so on the left-hand side I'm going to have 5 multiplied by -2 plus 1, and then we had a, and in brackets we had x minus 1, so I'm going to put -2 minus 1, plus b, and in brackets we had x plus 2. So I'm going to have -2 plus 2. Again, a similar thing happens this time with the b term. The b term becomes 0, and what we are left with is 5 times -2 plus 1, which gives us -9, equals -3a. That tells us now that a is equal to -9 divided by -3, which is 3. So if I scroll up here just to remind you what b was equal to, b we found was equal to 2. I'm going to scroll way to the beginning to remind you what it was we were doing. We were integrating 5x plus 1 over x squared plus x minus 2. So the integral of 5x plus 1 over x squared plus x minus 2 is equal to the integral of a over x plus 2 plus b over x minus 1. We discovered that b had a value of 2 and that a had a value of 3. And the reason why these integrals are the same, and I know that I might be going around in a little bit of a circular fashion here, but the reason is that we took this rational expression and rewrote it as the sum of these two. And by the way, if you want to bring these two back together with a common denominator to convince yourself that you get the original integrand, feel free. when you combine those two rational expressions, 3 over x plus 2 over x minus 1, you will get the rational expression that we started off with. So what this means, everybody, is that this integral which we were trying to find is exactly the same as this integral because those two integrands are equal to each other. So we're going to integrate the one on the right instead of the one on the left. The antiderivative of 3 over x plus 2 is 3 ln x plus 2, plus the antiderivative of 2 over x minus 1 is 2 ln x minus 1, plus our constant. And that's the answer. Briefly here, everybody, if you differentiated our answer, what it is going to give you is this, which means it's correct, because that integrand is the same as this integrand. So differentiating our answer gives us the original integrand. Let's try one more. Integrate 9x squared minus 6 over 2x minus 1, x plus 2, x minus 2. That means, everybody, since there are three linear factors, that this integrand of 9x squared minus 6 over 2x minus 1 times x plus 2 times x minus 2 must be equal to a sum of three partial fractions. A over 2x minus 1, b over x plus 2, and this time c over x minus 2. Notice that the degree on the top of this integrand is 2. The degree on the bottom would be the product of three linear, which would give us a degree of 3, which means this integral falls into the category of what we're learning today. First criteria is the degree on the top is smaller than the degree on the bottom. Second criteria is the bottom is factorable into all linear factors. Again, if either of those is not true, then that is something you would learn on Wednesday or Friday. So I need to eliminate all of those denominators by multiplying both sides of the equation by 2x minus 1, x plus 2, and x minus 2. Many of you will be able to do this almost in your head to get to the next line, but I do not want to lose anybody here. So I am actually going to take and rewrite the whole thing and show that I am multiplying every term in this equation by 2x minus 1, x plus 2, x minus 2. If I were doing this on paper, I would be able to write smaller and spread things out more. But because I'm on a smartboard, I had to kind of make things fit. What's going to happen is on the left-hand side, all of those factors cancel. I should just make one minor correction to what I have on the left-hand side. This 9x squared minus 6 is in brackets. So what is canceling is the 2x minus 1 and the 2x minus 1, the x plus 2 and the x plus 2, the x minus 2 and the x minus 2. When I get to the other side, the 2x minus 1 cancels with the 2x minus 1. The x plus 2 cancels with the x plus 2. And the x minus 2 cancels with the x minus 2. Which means that what we have left is the following. I have 9x squared minus 6 is equal to a multiplied by x plus 2 multiplied by x minus 2 plus b multiplied by 2x minus 1 multiplied by x minus 2 plus c multiplied by 2x minus 1 multiplied by x plus 2. And that is the equation that we have to use to determine the value of a, the value of b, and the value of c. So I am going to perform 3 substitutions here. One of the substitutions will be to let x equal 1/2. One of the substitutions will be to let x equal -2. And one of the substitutions will be to let x equal +2. When I let x equal 1/2, this term and this term will reduce to 0. Because when I put 1/2 in for x into 2x minus 1, 2 times 1/2 minus 1 will give me 0. And what that means is when I let x equal 1/2, I'll have an equation that contains a in it. When I let x equal -2, this term will go away, and so will the term that contains c, because -2 will make x plus 2 equal to 0 in the first and the third terms, which means when I let x equal -2, I'll be able to find b. And when I let x equals +2, the first term and the second term will disappear because they both contain an x minus 2. And that means I will be left with an equation that I can use to solve for c. So I'm choosing for values of x the numbers that are the zeros of the 3 different factors. On Wednesday, things will get a little bit more complicated, but again, for today's lesson, this will work. What's going to happen here is for letting x equals 1/2, I'm going to have, for an equation, 9 multiplied by 1/2 squared minus 6 equals a multiplied by 1/2 plus 2 multiplied by 1/2 minus 2. Don't forget that when x is 1/2, the term that contains b and the term that contains c reduce to 0. When I let x equals -2, the left-hand side becomes 9 multiplied by -2 squared minus 6. And on the right-hand side, the first term, the term with a, will disappear. And the third term, the term with c, will disappear. So all I will be left with is the term that contains b. And I will have 2 times -2 minus 1. And then multiplied by -2 minus 2. When I let x equals 2, the term that contains a will disappear because it contains an x minus 2. The term that contains b will disappear because it contains an x minus 2. The only term you will have left is the third term with a c. So I put +2 into the left side and get 9 times 2 squared minus 6 is equal to c multiplied by 2 times 2 minus 1, and then also multiplied by 2 plus 2. Okay, so I have a big edit in this video where I double-checked all of my work to this point. Then once I was sure that all of my work was correct, I put those numbers into my calculator. I basically divided this number by this number, and that gives me a equals 1. When I take on my calculator this number divided by this number, I get b equals 3/2. When I take this number divided by this number, what I end up with is c equals 5/2. Now, if you were to go back to where we started off with the rational expression 9x squared minus 6 over 2x minus 1, x plus 2, x minus 2. And we said that we're going to break it into three partial fractions of a over 2x minus 1 plus b over x plus 2 plus c over x minus 2. And the result of that investigation was that a equals 1, b equals 3 halves, and c equals 5 halves. What does this mean and how does it help us? Well, the integral we were trying to find was the integral of 9x squared minus 6 over 2x minus 1, x plus 2, x minus 2 dx. But since that rational expression is equal to a over 2x minus 1 plus b over x plus 2 plus c over x minus 2, we can now integrate instead a, which is 1, over 2x minus 1, plus b, which is 3 halves, over x plus 2, plus c, which is 5 halves, over x minus 2, and that is something that we can handle. It's really quite simple. So the antiderivative of 1 over 2x minus 1, by the way, it's not ln of 2x minus 1, it's 1/2 of ln of 2x minus 1. Because when you differentiate ln of 2x minus 1, you're going to end up multiplying by a 2 because of the chain rule, and we don't want that 2 there. Plus 3 halves times the natural logarithm of x plus 2, plus 5 halves multiplied by the natural logarithm of x minus 2, plus your constant. So the integral of 9x squared minus 6 over 2x minus 1, x plus 2, x minus 2 is equal to the expression I have on the right. In other words, everybody, this is our answer to the second example. There's a lot of work involved here, but the work is not anti-differentiating. The work is trying to do the algebra to break that rational expression into smaller pieces. And by the way, I just have another edit in here because what I did at this point in time is I went to Wolfram Alpha and entered in the integral of 9x squared minus 6 over 2x minus 1, x plus 2, x minus 2. It gives me a slightly different variation of the integral. So the answer is written a little bit differently, but it is in fact correct. All right, on page 35 of this handout are a number of integrals and a number of problems related to the method of partial fractions. Section A is not actually asking you to integrate anything. It is only asking you to change the rational expression into a sum of partial fractions. And I need to make a note to you that if you do want just practice dealing with that part of it, you only know how to do numbers 1 through 4 in part A. Sections B and C are asking you to find the actual integral, which means you have to go through this process of tearing apart the rational expression into a sum of partial fractions. But the only ones that you should be able to do based on today's work would be B numbers 1 through 7. And that's all you're expected to do in this modified version of the course. If you'd like to come along the road a little bit further with me on Wednesday and on Friday, I will be showing you how to integrate rational expressions that are more complicated. What if the degree in the numerator is higher or equal to the degree in the denominator? What if you can't factor the denominator into linear factors? And in all of those situations, there are different steps that need to be taken to resolve the rational expression that's the integrand into partial fractions that you can deal with as an integral. It's a pretty deep lesson. There's a lot of algebra going on and there's a lot of logic going on in what it is you're doing. So that's it. I hope you have a great rest of the day. I hope that some of you join me on Wednesday and on Friday. But for those of you that decide not to, I understand 100%. You're busy, you've got other things to take care of. But if you are interested, I will show you the other methods as well with partial fractions. Have a fantastic rest of the day, you guys, and we will talk to you soon.